This, as some of you have noticed, is our humble mascot, the anteater. It's not part of the native fauna of Southern California, but it was chosen as our mascot anyway.
Why?
60s, I don't know.
It's all over the place. Oh, yes, yes.
So this was supposed to be Stephen Goudreau's slot, as I mentioned yesterday, but he couldn't make it due to medical issues. So, so you'll get me instead, trick or treat. You can tell me which one of those it is after the talk. But so I'm also affiliated with YASA, as I mentioned yesterday, which is the International Institute for Applied Systems Analysis. And I'd like to thank YASA. A lot of the work I'm going to tell you about was done at YASA over the last several summers. I'd also like to thank NIH Fogarty, who the folks there who've been working on flu I've also been working with, and I've learned a lot from them. This work is partly joint with Cecile Vaboud from NIH and partly with my student in Nguyen from here at UCI. This is kind of a mishmash of two different projects on flu that I'll be talking about. Some of you have seen some of this before. I gave a talk based on some of this at David's group at the CDC almost exactly a year ago. And Justin saw some of this at a poster at the Options Conference in Hong Kong. So, but I've improved it since then. So, some of these slides are based on my talks at demography departments around the country. So I'm going to skip a lot of the sort of exposition on flu because we've already heard a lot about that, and this audience already knows a lot about that. But I'm going to be talking about influenza and P&I both. So it's important to note the distinction. I'm a demographer of human mortality, and influenza is a cause of death, and pneumonia is also a cause of death, and these two are often analyzed together as P&I, as it's called in the flu world. And influenza, when it's fatal, kills through pneumonia. But pneumonia, not all pneumonias are caused by influenza. So this causes a problem when analyzing mortality statistics, because some deaths are coded as influenza explicitly, and some deaths are simply coded as pneumonia. And I'll show the ICD codes in a minute. But it's important to note the distinction. And when I say influenza, I usually mean influenza. When I say P&I, I normally mean both combined. So my co-author for part of this work, Ian Nguyen, just entered the room. Hello. And I'm going to be talking about changes in old age, P&I mortality. Well, from 1959 to 2007. And you'll see what I mean, Don. And needless to say to this audience, because you guys aren't shy, as we saw yesterday, but I welcome clarificatory interruptions. So I'm going to skip the sort of basic stuff about flu, which you guys already know. So in the 19th century, we had, we believe, H2N something for the first part from 1889 to 1898, and then in 1899 to 1917, we think that there was H3N something. We don't really know definitively at all what was circulating before 1918. In 1918, we had the emergence of H1N1, and that we do know because we have samples from 1918 onward. And so the reason why the numbering scheme begins at H1N1 with 1918 is when flu virology really became a modern science. It was long after 1918, and so they just started numbering with the types that they had, on hand at the time. In 57, there was the emergence of H2N2. It's the so-called Asian flu. And in 68, we had the emergence of the so-called Hong Kong flu, H3N2. And so the data set I have is 59 to 2007. And as David mentioned yesterday, there was a 3-year delay in the release of the final, I believe you mentioned that, in the final mortality statistics. So I don't have the 2009 data yet. Nobody does. And so even though I have almost a 50-year time span, I only have one pandemic in there, and that's the Hong Kong H3N2 outbreak. So I'll be talking a bit about that. The NCHS releases the data when they consider it to be final. And I mentioned yesterday that sometimes even after states find some missing death certificates, they don't modify what is considered to be a final data release. But they do not release any data before it's final. So even if I wanted to, I could not analyze sort of the 49 states plus DC for up to 2009 now, and then just add California when California gets released, because that's not how it works. The NCHS, which is the clearinghouse for the 51 data sets, releases it when it's considered final. So I don't have, and nobody will have, the final mortality data from 2009 until sometime around late August of next year, because about 6 weeks ago they released the 2008 final data. So in 1977 we had the reintroduction of H1N1, which is believed to have been a lab escape from a Russian lab. And one of the curious things is it used to be that when a major strain emerged in a pandemic, that it would displace the existing strain. So a vulgar functionalist such as Jamie would say, that it outcompetes the existing strain in a Darwinian fitness kind of sense. So when H2N2 emerged in 57, H1N1 disappeared. And when H3N2 emerged in 68, H2N2 disappeared. But in 77, when H1N1 was reintroduced from this glassware escape and spread around the world, we have had since 1977 co-circulation of both H3N2 and H1N1. And that's rather interesting. And then when a new strain of H1N1 emerged in 2009, the so-called swine origin influenza virus H1N1, that seems to have displaced the 77 and onward strain of H1N1, but not the H3N2. So ever since 68, we've had co-circulation, well, ever since 77, we've had co-circulation of H1N1 and H3N2. But before that, strains seem to have displaced each other. So that's kind of an interesting, I don't know exactly why this is. Maybe this is something we can all discuss in the open session this afternoon. But it's a really fascinating aspect of flu virology. No one was expecting that the pandemic would be H1N1, because up until then, pandemics had always been a new major strain emergence. And one of the reasons why the pandemic was relatively mild is probably that there was H1N1 in circulation ever since 1977, and there's probably some cross-protection. And before 57 as well, there was H1N1. So a large swaths of the world population have seen H1N1 before, even if they haven't seen this particular H1N1. So a lot of what I'm going to be talking about is the seasonality of flu. Seasonality of flu, I will submit, is poorly understood. Because when you take a bird's eye view of the literature, there's different strands of the literature that all claim that it's well understood, but well understood by a different mechanism. So everyone has their own sort of pet theory. My machine's Linux, so that definitely wasn't me. I don't know what that was. sunlight, humidity, temperature, school year, dynamic resonance, host defenses have all been proposed as mechanisms that drive this seasonality. So sunlight, typically is supposed to work through vitamin D production, photosynthesis of vitamin D, which stimulates the immune system. And so in the northern hemisphere, well, in the temperate hemispheres, we have very little UV exposure during the winter time. Yeah.
You're familiar with Jeff Shaman's?
The absolute versus relative humidity stuff, yeah. That's kind of a hand wave, if you ask me, but
What's that?
it's, yeah.
Yeah, all right. I'm just curious what you think of it.
Well, I mean, the humidity stuff, so humidity in the northern hemisphere, in the hemispheres is very correlated with these other effects, and I'm just not persuaded that it's as easy to tease out the competing causality as some of the folks seem to think it is. So there's a group that claims that absolute humidity is extremely correlated with influenza incidence and mortality, and that relative humidity doesn't work. But if you convert everything to absolute humidity, I mean, I don't see. There's no real persuasive mechanism that sort of explains.
Well, the mechanism that they propose is the evaporation of droplets.
Right. I know, but that's a hand wave. Like as Justin mentioned yesterday, in the tropics, there's year-round transmission of influenza.
Yeah.
It doesn't. To me, it doesn't sort of add up. We can talk about that. But yeah, in fact, the tropics is sort of a mystery, and to me, I think we're going to understand a lot about the basic bio of flu by understanding it better in the tropics, because there's some people who believe that there's lots of questions about the tropics, and the tropics are an interesting experiment because you have flu transmission, but you don't have this seasonality, and so I think you can learn a lot about that. I don't see why these. If you push these people, and I haven't talked to Jeff about it, but I've talked to his co-author Mark Lipsitch, and if you push them hard enough, they start to say things like, well, the flu works differently in the tropics than in the temperate hemispheres, which it's the basic biology shouldn't be all that different, right? It's the same virus, it's the same host. The ambient temperature is higher, the UV exposure is different, but the humidity is different. But how much different is the pathology once the virus enters the host? So I just find that I'm unpersuaded by the humidity stuff.
I asked just because I'm rarely in a room with physicists and engineers who know something about
Yeah, well, I'm sure there are people here who know much more about the.
In sewage treatment, which depends on the bacterial population in the water, you have a different population in places like South Africa and South America than you do in the north. So you get the design, America or northern designs for sewage treatment plants don't work because they're certain.
Well, because the water runs the wrong way down the.
Maybe the bacteria don't they like the spin.
Well, but flu is a virus, so we're not talking about different floral populations, right? So it's the same virus.
And the other factor is sort of how susceptible you can be. So if it's cold, your skin cracks, get infected there, and your lungs are maybe a little more susceptible. So I think there are two competing effects. But it always is interesting in the tropics. But then, you also don't heal as well in the tropics. The sores stay open a lot longer. So I think a lot of it's probably immune response.
And so some of the things I've thought about for the tropics is also perhaps the role of fomite transmission might be slightly different in the tropics due to surface temperatures or humidity levels. And then some have proposed that the northern hemisphere, which has sort of plays a large role in influenza or it's postulated to play a large role in influenza. That the hemispheres may be, the tropics may be somehow reflecting what's going on in the hemispheres in a sort of complicated way. So there's a paper by Vladimir Alonso looking at Brazil, where he seems to suggest that the populous North America and flu situation is somehow affecting Brazil. I'm not sure I believe that either, but so I study flu mortality. As I said, it's the 8th leading cause of death. It's kind of
I really mean flu and pneumonia.
yeah. So flu and pneumonia is the 8th leading cause of death. Sorry, I said I was going to be specific, and now I'm being vague. Yeah, flu and pneumonia together is the 8th leading cause of death. Flu itself is way down there. It's the last remnant of what demographers call the epidemiological transition. So in the 19th century, infectious causes of death used to be the number one killer. And we've moved to a regime of chronic causes of death, like heart disease and cancer being the number one killer. And the influenza and pneumonia is the last leading cause of death that's entirely infectious in origin. So mortality is a more definitive outcome than ILI, influenza-like illness. That's one of the attractivenesses of studying mortality. If someone dies, you have it's a definite event. You have a death certificate that's generated, even in California, and flu-like illness is much more vague. But as I will show, mortality is not without its own pitfalls. In fact, I used to think that mortality was a much better measured outcome. Now, the more I studied it, the less sure I am about that. I think it has some different downsides than ILI and some strengths relative to ILI, but also it has its own weaknesses that we should not ignore. The demographers and epidemiologists approach the problem quite differently. I'm going to be talking about death certificate P&I mortality. So I'm going to be talking about basically mortality that gets recorded on the death certificate as pneumonia or influenza and gets forwarded to the NCHS, even by California. Epidemiologists are often worried about excess mortality. So there's some baseline that's calculated, and then we subtract that baseline off the actual data, and what's left is excess. And that is what classically epidemiologists call flu mortality. And then, there's all sorts of, I don't want to get too sidetracked by it, but there's all sorts of intricacies in how that calculation is done. The winter peaks are actually not fitted. It's only the summer troughs that are fitted. And so the baseline is meant to represent the cyclical pattern of P&I mortality that you would see if only the summertime pattern were dominant all year round. And then we know that there's very little, if any, flu virus in actual circulation in the summer. So that's what justifies the assumption that you can completely subtract off that baseline, because flu kind of troughs in the summertime, and therefore it presumably peaks in the wintertime, but there's actually no flu virus causing that trough. So whatever peak is implied by that is presumably also not due to flu virus. So you calculate the baseline that way, subtract it off, and then typically you have excess over that, and that's imputed to be due to flu virus. The way the models are usually run, the flu season is predicted to peak in the same month every winter, which is certainly not the case. So that's another issue. Mortality, as demographers define it, is a quantity that's greater than or equal to 0. Excess mortality can be negative, and often is. So I've already mentioned flu versus P&I. So if you just look at flu deaths that are classified as flu deaths per se, you clearly have an underestimate of flu mortality, since a lot of people filling out the death certificate will write pneumonia if they have no specific evidence of flu, even though we know that in many of those cases there must be flu. Although pneumonia itself is caused by other pathogens such as pneumococcus, a bacterium. So, you know, we clearly know that if we that not every pneumonia death is a flu death. So we have this sort of contrasting problems of choosing an underestimate versus an overestimate, and the Surfling regression is meant to sort of address that, but it's a very model-based approach, so it has sort of all the pitfalls of model-based approaches for those of us who like to stick to the data. I mean, and when it's applied to all-cause mortality, it can give some pretty high estimates for influenza attributable mortality that, you know, I think are a little bit unbelievable. But I don't know why heart disease deaths peak in the wintertime in the temperate regions. I mean, and it's certainly plausible that circulating respiratory viruses, and flu is probably the most prominent of those, are somehow playing a causal role in the wintertime peak of cardiovascular mortality. But you know, heart disease, cardiovascular mortality is about a quarter of all deaths, and they're cyclical with winter peaks. And so, if you want to start fitting flu peaks to those peaks and then attributing causality to a lot of the excess wintertime heart disease deaths, you can get, you know, really huge numbers of flu-related deaths that I'm not sure are all actually causally related to flu. I think what the NIH should do is a large random sample autopsy study where we actually take a look at a lot of these heart disease deaths and look for the presence of flu virus, and that would cost a lot of money. Yes, David?
Yeah, that would never be done, though.
Of,
what you just
yeah.
said. I mean, it's not realistic to expect, because the problem would be, even if people were able to sample these incident deaths for flu, is that for perhaps even a majority of these cases, the outcome would be so removed from the flu virus infection, maybe by 1 week or 2 weeks or 3 weeks, such that even with PCR techniques you could not detect flu, even if it were sort of the influential in terms of the ultimate cause of death. You're still not going to be able to pick up flu.
I take your point. I mean, I certainly take your first point that it will never be done because it's too costly to do a large enough sample size autopsy study. I mean,
well, I mean,
so, but
it's
you.
going to be done in the U.S. There are places that probably.
There are ways around. You could do like a large cohort study where you, look for flu antibodies at the beginning of every flu season, and then those who die get. Yeah, you could. Well, we can talk about that later. I mean, I take your point that the virus will have cleared, and that even with PCR you won't be able to find any. But I mean, with serial serology, you should be able to tell if they were killed by a recent flu strain, if they were infected with a recent flu strain, right? But it would be. I mean, it would be. That's kind of a pie in the sky kind of study that will never be done. But so the American Journal of Public Health, which is I don't know, it's a pretty good journal, I think, published a critique of the way both demographers and epidemiologists are doing this by Peter Doshai, who was at MIT at the time. And he said, well, flu estimates are totally overblown by everybody, both demographers and epidemiologists, because you're looking at pneumonia deaths and we don't know that pneumonia deaths are flu deaths, and therefore none of them are flu deaths. That's basically sort of a cruel summary of his work. And so in some sense, what I'm about to show you, some work that Ann and I did, is sort of a reply to that. We're using microdata on every death from the NCHS. We have underlying and contributory causes of death, although for this work we're only using the underlying cause. We have monthly time resolution. So we have deaths by age and sex and month of occurrence. We extracted all influenza and pneumonia mortality from these data files. So these data files are released usually every August, There's nowadays about 2.2 million deaths in the United States, and so the NCHS releases a flat ASCII file with 2.2 million lines, each line representing coded data from a death certificate. So there's about 2 gigabytes of mortality data released every year by the NCHS. And so we extracted all these data. We adjusted for changes in ICD. So there have been 4 revisions of the international classifications of death and disease during this time period. So we used the published crossover tables by age and sex to correct for those changes. And when we've calculated rates, we've gotten exposure data from the human mortality database interpolated to months. So the human mortality database is a large online repository of international mortality data, and the person years at risk, the denominators of our rates, come from the HMD, which is better than using census data because they've already adjusted for information on exactly when people died and when they were born, from Social Security Administration, which is not publicly available, but it's available to the HMD. So they've sort of fine-tuned the exposure data in ways that are far better than just downloading data from the census in terms of how many people there are in each group, which demographers call exposure. I interpolated those to months. Sometimes in the literature, demographers just divide everything by 12. That's not good enough because February has 10% fewer deaths than the months around it because it has 10% fewer days. So you get weird things happening if you don't adjust for days and leap years in addition. So here are the causes of death we use. So as I said, there have been 4 revisions of the ICD. Yesterday, David was talking about data from the 1990s, so he was talking about ICD-9. We're now on to ICD-10, so there's 2 causes of flu under ICD-10 and so on. So when I say influenza, I mean this, and when I say pneumonia, I mean these. And when I say P&I, I mean both. So here's the age standardized death rate for this is P&I, okay? In the last 50 years, these vertical dashes represent the changes in ICD regime, although, as I said, I have corrected for the changes, so you shouldn't and you don't see any strange changes in level corresponding to these dashed vertical rules. Men and women, we can see, have quite different death rates. The mortality schedules for men and women are sort of transposed horizontally, so to speak, relative to each other. So men have higher mortality rates, so they're more or less equivalent to older women. And it's almost always the case that mortality data should be analyzed separately by sex, because when you sort of glom them both together, you just get sort of a mongrel that is representative of no actual human subpopulation. So everything should be analyzed by sex. And I even convinced Lona Simonson, who's a very prolific author in the flu literature, that data should be analyzed separately by sex. And for those of you who know her, convincing her of anything can be quite a task. So I was really pleased about that. But anyway, so now here are just the numerators. These are influenza and pneumonia deaths for women. So the red series are pneumonia deaths, and the green series are influenza deaths. Influenza deaths refer to the axes on the right, and flu deaths, pneumonia deaths refer to the axes on the left. So David showed some of these exact same data yesterday. This is all the data we have from 1959 to December 2007, and I mean, we can see that these data are in remarkable lockstep with each other. They peak sort of at the same time every year. Influenza is diminishing in its use as a cause of death. So in the 60s, all the winter peaks and summer troughs of flu classified mortality is, it is on the order of, in the summer troughs on the order of 10 deaths per month per sex in the United States. And as we move down to more recent years, we see these gaps where there are no deaths classified for an entire month that were called influenza. So no one essentially dies of influenza in the summertime anymore. And so yeah, and we see the same for men. We see slightly higher numbers of deaths for men, but it's the same pattern of declining numbers of deaths, both for flu and pneumonia. Now, Peter Doshai is really only interested in the green time series. And he published a paper in the AJPH where he looked at the green time series and said, flu is totally a cause of death that's in decline and we don't need to worry about it. And as David mentioned yesterday, that there are some years in which flu does whatever it does, but P&I seems to stay the same relative to the years around it. And so that got Ann and I thinking about, that exact kind of variability, and we decided to look at the proportion of all P&I mortality that is explicitly coded as influenza. So just a simple I over P&I measure. And this has the advantage of that if you're looking at this in terms of numerators or rates, it's the same quantity because the rates are present in both the numerator and denominator of this fraction, and they therefore just cancel each other out. So the numerators are pretty well measured, even with California, and the denominators, what we use to calculate rates, are based on censuses which are only collected once every 10 years and which are only good to a few percent anyway, et cetera, et cetera. So I'm a much bigger fan of the numerator data quality than I am of the denominator data quality. So I'm really happy whenever I can just dismiss the denominators. So this is the quantity I over P&I for the time period for the last 50 years or so. And we see that the proportion flu peaks in the wintertime. That's not surprising because, as I said, there's very little flu virus in circulation in the summertime. But it's really quite variable, and it's, the proportional use of flu on the death certificate has diminished completely in recent years, or almost completely in recent years. So there's a few years that we've shaded here. That this reasonably high use of flu is the Hong Kong pandemic, and this is the global maximum of the use of flu on the death certificate, and that was during the 1976 swine flu scare. Scare. This was not an actual flu outbreak, except for one very unfortunate soldier in New Jersey. For everyone else, it was a scare, but not a real outbreak. And yet, of all P&I mortality in the spring of 1976, 50% of it was explicitly coded as flu, which could not have been, I don't think, laboratory confirmed anyway. Then in '78, we had the Russian flu scare. Yes, Michael?
So Andrew, let me ask you, according to the definition
Mm-hmm.
of these tables, you said that flu kills by pneumonia.
Yes.
So should technically all these be listed as pneumonia, since flu doesn't actually kill people?
They could all be listed as pneumonia, but according to the...
What are they supposed to be doing?
Well, that...
Now people are just following the rules. Flu doesn't kill people, so they don't listen.
no, that's almost certainly what's going on. I mean, in terms, I mean, there's no, flu is there's no viremia in flu. There's no bloodstream, presence of influenza virus. It's a respiratory tract infection, and the flu virus jumps from one epithelial cell to another in the respiratory tract. And if it makes it to the lungs, you get a pneumonia, there's primary influenza pneumonia, and then there's secondary bacterial pneumonia where. But basically, if flu kills you, it kills you through pneumonia. And so every flu death could be coded as a pneumonia death. But the protocol is supposed to be that if the person filling out the death certificate, it's not always a doctor, But if the person in the United States is certainly not always a doctor who fills out the death certificate. But if influenza is known to be the cause of the pneumonia, then it's supposed to be recorded as influenza. So if there's a lab test that says this person had flu, then the proper thing to do is write influenza. I mean, because the ICD is meant to be highly detailed. I mean, if you...
it's contributory or it's underlying?
It would be underlying in that case. It would be underlying in that case. But there's a lot of, I mean, the way death certificates are actually filled out is often by a nursing home director or a funeral home director, or, you know, it's not always a doctor who has, you know, been caring for this patient for the last fortnight or whatever who fills out the death certificate. So there's a lot of, sort of, there's the way things are supposed to happen, and then there's the way things actually happen, right? And so even in states other than California, someone other than a physician is going to be filling out the death certificate a lot of the time. So, so in '78 we had the Russian flu scare. This is the glassware escape of H1N1, which was quite prominent in the medical literature at the time. If you read the New England Journal of Medicine or the Lancet from 1978, there's a lot of talk about, and there was a paper in Nature, a lot of talk about, you know, oh my God, H1N1 is back. So what happens? Influenza as a proportion peaks again. Then in 1981, this is the last ever year in which influenza was at least a quarter of all flu deaths on the death certificate. Ever since '81, influenza has never reached a quarter of all wintertime flu deaths. But there's just a general movement towards pneumonia. As you say, people are just going more vague, even though we have probably more lab testing than ever before. In the last few years, since about 2001, you know, there's been hardly any explicit use of influenza on the death certificate, except for the vaccine shortage in the fall of 2003, when again influenza was big in the medical news. And then we have another little peak of this quantity, I over P and I, and it peaks earlier in this year than it normally does, and that also corresponds to this vaccine shortage, which was all the talk of the medical news in September and October of 2003. And then the following winter, which, as I'm sure many of us remember, was the bird flu scare, H5N1, which was going to be the big bad pandemic. It again kind of peaks, and then it goes back to sort of oblivion. I'm really desperate to see what happens in 2009 when we have the H1N1 pandemic. I'm dying to see, no pun intended, what happens to the proportion of I over P and I. So, I mean, basically, I think, Dr. Doshai has not really, I don't think, put his finger on the right aspect of the problems with influenza time series. It's not that we've been looking at P and I and we should just be looking at I. I mean, it's just that there's a lot of data issues when you drill down into the details of how the deaths are collected and classified. And, you know, sort of, you know, fads and, you know, beliefs within the medical profession are as influential in what gets recorded as is the actual, you know, circulating virus situation. And throughout all these changes, the P and I death rate isn't changing anywhere near as drastically. So the best practice really is to use, whether or not you're going to calculate excess mortality or just analyze the explicit data the way demographers do, the best practice is to use P and I, okay? Influenza and pneumonia. Now I'm going to switch gears away from these sort of data quality issues. So that paper's under review at Biodemography and Social Biology, which is a demography journal. I'd be happy to send copies to anyone. And I'm going to talk now about the work I'm doing with Cecile Vaboud at NIH. So we're using P and I, you know, having conducted that data exercise, we're going to use P and I, not influenza only. And we're analyzing the incidence of P and I mortality basically over the age domain. This is the time series, as I showed you before, of the age standardized death rate of P and I. The age-standardized death rate is simply a weighted average of death rates at all ages. And since the same weights are used every year, the changing age structure of the population is therefore standardized out. But it doesn't give you information on the age structure. It's really just taking all the age information and collapsing it down. And so we have this nice-looking time series, but we don't know what's going on within the age structure of the population. And demographers are kind of obsessed with age. In fact, when kind of pressed for a definition of demography, demographers often sort of resort to, well, it's the study of something by age, right? Isn't that true? Because people kind of go, well, how's demography different than, quantitative sociology? Or, I mean, and people often say, well, it's age, right? No, Jamie doesn't agree, but no, space is geography.
I don't know. Vital events by structure.
Age structure is the most often structure is age, and in my opinion, we'll talk about this later. That's fine. So we've got all these age groups, and the age standardized death rate just sort of compresses that and doesn't really do it. So what demographers often do is some sort of model of the incidence of mortality by age. So the Gompertz model is simply exponentially increasing mortality by age. So X is age. Alpha and beta are parameters to be estimated from the data. And I mean, the left-hand side of the equation is in the sort of classic formulation is the life table hazard rate. But I mean, people often just sort of substitute any kind of mortality for h of x. So just observed mortality rates or logistic regression mortality from a sample or something is often substituted for the left-hand side of that equation. And this is estimated typically by logging both sides and just doing OLS on the resulting data. Although you do get slightly different estimates if you do nonlinear least squares on this equation in its original form. And the reason being that the way the error term is treated. And no one seems to ever worry about that for some reason in demography, but except for you. Okay. Well, great. We have something to talk about later. But anyway, but there is a difference, and sort of the customary way to do this is to log both sides and do OLS. So that's the way I've done it. So Gompertz mortality is obviously therefore monotonically increasing, and therefore it's an old age mortality model, Don. So from age about 45 on up, there's a constant sort of linear increase in log mortality. So basically, Don, if you're above age 50, you're old age from the point of view of. So we're looking at death rates by in 10 5-year age groups, 50 to 99. Demographers group everything into 5-year age groups because of heaping at single years of age. Well, so there are more deaths at age 50, 55, 60, 65, and so on than you would expect. So, and I blame California for this, but basically in the death certificates there seems to be just inaccuracies in recording, that you get all these strange sort of what we call heaping effects, that there are more people at round numbers of age dying than you would ever expect from the distribution of the population. Right. So we do everything we analyze all the data by 5-year age groups, and then if we need more detail after that, we interpolate the results by a spline or something. But we don't just chop everything into single years of age and analyze that, because you get all these jumps that are just not believed to be actual data. They're just artifacts.
Do you really believe that's artifact, not?
We do, yeah.
It's not like a milestone. I made it 60. It's good enough.
So it happens in all sorts of reporting things like this. So with sex partners, if you plot the number of yearly or lifetime sex partners, what you necessarily who's filling out your death certificate.
Yeah.
Right?
No, it's something it's sort of strangely pervasive through all sorts of vital statistics. I mean, although maybe people stop after a certain number of sex partners, right? Like, because,
Well,
but.
don't tell
Nobody's going to comment on that.
Okay.
No, I'll comment for hours.
Anyway, and then we use some centering stats. So within each 5-year age group, we don't just we use the empirical average age as the X value. So we don't just use 57.5. We use the actual. I'm actually running out of time, so I'm going to sort of accelerate here, just as the mortality is being accelerated. So let me show you some pictures, and you'll see what I mean. So here are the death rates by age for men and women. The size of the circle is proportional. The area of the circle is proportional to the number of deaths in the cell, and the summer mortality is here with these dashed lines and open circles, and the winter mortality is with the solid lines and filled circles. And we see basically a really good log linear relationship here, which is indicative of a Gompertz relationship. And moreover, that most of the flu deaths most of the P&I deaths are age 75 or over. So I don't know if that makes you feel better, Don, but.
But you say it's proportional. You mean proportional to the number of the cohort still alive?
No, the absolute number of deaths occurring. Yeah.
Okay, so the smaller ones up there around age 95 means there aren't very many people 95.
That's right. You don't. Not that many people live to be 95. So. And then here is just another year. I mean, I could go through all these years, but so basically, my original interest in this was sort of how we can describe this age mortality landscape by these two parameters, alpha and beta, which are the sort of key things in the Gompertz model. So we see that that the alpha parameter has sort of declined and then started to rise again in recent years. This is the level parameter of the Gompertz model. And summers and winters are pretty close to each other, except for, actually, which is quite interesting, except for around the Hong Kong flu pandemic and a few years thereafter. We see something similar for the slope parameter. When the level parameter goes down, the slope parameter goes up. And summers and winters are pretty similar. And the 68 pandemic had a very unusual slope parameter. Gompertz is quite a good fit. Justin, this was your idea to plot the R-squared this way. I don't know if you remember, but you told me when you looked at my poster. I mean, the R-squared is, even in this year, which is the Hong Kong flu, which is not a good fit, we have an R-squared still of over 97%, and usually it's up, over 99%. So, the Gompertz is a good fit to the flu data. And as I showed you, so here we have summer and winter and males and females, and the alpha and beta, these two parameters of the Gompertz model, actually are in a really tight fit with each other. I mean, so much so that it looks just like almost a perfect line here. So what's going on here is we have sort of an age-sparing effect, so that there's a reason why that's the case. That when the intercept is lower, the slope gets steeper. So in the Hong Kong flu pandemic, we have higher death rates at younger ages. So we see here, here's the pandemic. These open circles are the pandemic, and the filled circles are the previous winter. So the pandemic results in an increase in death rates at younger ages, and not much change in death rates at older ages. And that's, so we can see here's 67, and then here's 68. These are death rates by month. So we see a jump in these death rates at relatively modest ages. I mean, in the 30s, 40s, and 50s, we're seeing higher P9 death rates. And so basically, I'm just going to run through this really quickly, but what I'm doing here is I'm trying to take apart this variation within this sort of tube here, and I'm gonna rotate this. So 99% of this graph here is white space on either side, and so you can't really see what's going on. So I'm gonna just rotate the data so that we can see what's going on, and here we get a better sense of the variation. And each color code is different for the strain of flu that was in circulation. So here's, and the axes aren't labeled anymore because they no longer mean anything because I've rotated everything. So yellow is H1N1, and so we see the parameter space jumping around a little bit, and then we see the introduction of the H3N2 in green, and it's sort of out at the edge of this convex hull here. But then we see, that the green moves right back into this area where the yellows were. So you can already see that you cannot sort of define a region of this mortality space exclusively based on the strain circulation, because we have almost identical Gompertzian mortality, whether it's H1N1 or H3N2 in this region. And then mortality is just in general declining in the US, so we're moving towards the left of this graph over time. And so that basically, the bottom line is that the Gompertz mortality model really collapses down to one parameter for flu and pneumonia. Yes?
So I'll point out this covariation of alpha and beta in physical chemistry, that's called the compensation effect.
Uh-huh.
And they put the pre-exponential factor and the activation.
Mm-hmm.
And basically what that's saying is your data almost fit your exponential line.
Mm-hmm.
They almost fit the line,
Right.
but not quite. And the fact that they almost fit the line, that's what makes the alpha, puts a constraint on the alpha and beta being very similar. So it's called the compensation.
Compensation effect in physical chemistry.
Yeah.
I'll email you about that. Thanks. That's why we have so many people from different backgrounds here, because I never think about physical chemistry. And so basically, well, I sort of think I want to modify this. This is about the secular decline being mostly about levels and not in slope. I mean, the two are so closely intertwined that it's hard to say that one or another is in the driver's seat. But what I really think is going on here is that at older ages, say about 80 and up, the flu mortality is changing very little from year to year. Pandemics or not pandemics, it stays the same. It seems to be sort of beyond a certain age, mortality rates for various causes start to look just a lot like the all-cause mortality rate. So there's a certain failure rate in the human mechanism above a certain age, and regardless of what whoever, thanks for coming, Michael, regardless of what whoever writes on the death certificate as the cause, there's just a certain failure rate of humans beyond a certain age. And where P&I mortality is very sensitive to what's going on in the viral situation is at the sort of older but older age, between about 50 and about age 70. And what we see is that when there's a novel strain of flu, those death rates are very sensitive to that. So they pivot upwards. And then that's how come you get changes in alpha and beta at the pandemics, because it's really about the pivoting of the younger age groups, presumably because they have less viral exposure over the course of a shorter lifetime. And also because they're not just sort of being grouped in the old age mortality group. One extension of this that I'm going to do with Jesus Crespo of YASA is what we're calling PGEC, piecewise Gompertz with endogenous cut points. So we're going to do Gompertz for 50 to 70 and 70 to 100, but the exact pivot point is going to be identified by the data, so it's not always going to be 50 to 70. So that's an extension of the model that we're really excited about. But basically novel viruses skew younger. I mean, that's the take-home message from this. And I mean, one interesting question about that is if it's just that you're a younger person and therefore haven't seen as many viruses, and therefore you're cross-immune to fewer viruses, and therefore your mortality goes up when the pandemic comes. That's a bit of a hand wave, because as we saw yesterday in Justin's talk, that the age 7 or 8 seems to be an important pivot point in the human immune response, and we know that these, the viruses that you're exposed to after about age 60 probably aren't stimulating your immune system very much, so it's not clear why the 80-year-olds should have such a different response than the 60-year-olds to these novel flu viruses, because between 60 and 80 you're not adding that much. Even though you're being exposed to 20 more years of viruses, your immune system is so sort of calm by then that you're not really generating that much cross-immunity according to the theory. So that might well be an important factor. So there's a lot of moving parts in this in terms of demography and immunology, and I don't claim that we've sort of figured it all out, but I can definitely say the demography agrees with the epidemiology that novel viruses skew younger. So I know I've run over time, but thank you very much.
Lunchtime flexibility, I think, so we can take a few questions. So what about if we old parts,
Speak for yourself,
we old parts have the death rate seems to be what you'd expect from whether, independent of the influenza. Does that say anything about whether or not we should be getting vaccines at 60 or 70?
Well,
Not going to make a big difference.
I mean, I once said in print that, that the most people who die from P&I are older folks, and that therefore they have probably the most to benefit from vaccines. But I'm not sure I would say. Well, I'm not. I was going to say why I said I once said that in print. I'm not sure I would say the same thing if asked today. I mean, one thing we know is that we give about 100 million doses of vaccine in this country every year, probably more now, right? 120 maybe, and most of them go to the age 65 and up.
Yeah. So if there were a real shortage, I mean, if we had a scare of age 12 and 65 that we weren't expecting.
There is no known 65 neuraminidase, but one question you have to ask is how much immunogenicity does the vaccine have, in an 85-year-old man? And the other thing, and the Japanese, and I'm sure David knows a lot more about this, but the Japanese have been really exploring, and people, I think increasingly in the U.S. have been asking this question, is rather than vaccinating grandma and grandpa, why don't you vaccinate the grandkids who are going to potentially bring the virus to the nursing home?
Yeah, James said so.
So this is a paper I should have submitted like 6 years ago, but I didn't for various reasons. But you look at the next generation matrix for an age-structured flu transition model or whatever model, right? You calculate, it's an asymptotic thing, right? It's linear, it's the linearized system, whatever. It gives you information about, it's analogous to what you get in a demographic model. You calculate the elasticities of this, right? And which is just a proportional sensitivity. It's a change on a log scale of
Percent change.
Yeah, and if you do this using Ira Longini's Tecumseh data, which I know, Carl, you've been highly involved with too, right? That and the elasticities of all the elements, the pairwise transmission, sum to 1. Overwhelmingly, 40% of all the transmission bang for the buck there is in school-age children. And so if you want to protect grandma and grandpa, vaccinate in the schools.
Yeah.
Right.
That is what
I think we're hearing that reinforced triple.
Yeah.
Which may not, which wasn't the story at H1N1. I think wasn't the emphasis, let's save the vaccines for the
older
seniors.
ones. Yeah.
Well, no, not for this past pandemic, it really wasn't.
Yeah.
Okay, the
My
stories that we heard were.
No.
My recollection jives with what Dave. My recollection jives with that they were trying to vaccinate. They were actually trying to do that in H1N1.
Yeah, and we did an interesting sort of, it was almost an experiment with how they were going to use the federally allocated vaccine. Maine decided to give vaccine almost entirely to school-age kids. Maine also was sort of unique in that the peak of the disease, because they were way up there, was sort of a little bit later than the U.S. as a whole. So they had an opportunity to sort of, or potentially decrease transmission because of the vaccine program, which was not the case in most of the regions in the U.S. where disease peaked way before vaccine was available. So we very excitedly went up to Maine and tried to look at what happened. And there is some suggestion that vaccinating school-age kids in Maine did decrease transmission of flu. But it's not unexpectedly. It wasn't. I'm just a general skeptic. It didn't work like it was supposed to. It didn't work like the model said it would.
Let's go back to Carl's question. At what age should you say, well, maybe I don't need the vaccine anymore? For example, I just got vaccinated 2 days ago, all right? And he asked me if I wanted it, and I said no. And then he said, why not? I thought about it for a while, and I took it only for public good question. That I'm not going to be a free rider type. But I didn't think I needed it for myself, for some of the same reasons that Andrews was just, for the figures that he's just showing. So what age should we stop?
Well, I mean, you're asking a tough question. So are you asking the question in terms of personal sort of utility or utility for the population as a whole?
Well, population as a whole is why I got the shot, not the personal utility.
Well, but that's not the way most people think.
I know.
Let's, we can continue this a little later. Time is maybe while Jim's getting his presentation ready, we can grab a cup of coffee and maybe some stuff to throw at him in case we get angry.